Chapter 9 is an important chapter, in fact, because let me tell you later on, for those of you who will be with the structural engineering major or aerospace engineering major, most likely you have to deal with moment of inertia very, very frequently. Again, that's the basic parameter to characterize how rigid that beam structure is. Because we talk about the bending rigidity, or in short, we call the flexural rigidity. That's basically E times I. E is a Young's modulus, or elastic modulus, or elastic stiffness, and I is the moment of inertia. So that's why that parameter is very important. It's much more important than centroid, in fact. Okay. So this chapter basically tells you a simple way to calculate the moment of inertia. Although in later courses, when you enter junior, like a 150, 151A for civil engineering students, we're going to continue to talk about moment of inertia. Okay, so this chapter is basically give you a simple idea to calculate a new concept, which is called the moment of inertia. So this one, in fact, is a moment of inertia, which by definition is integration y squared dA, which is the moment of inertia with respect to x-axis. Then, of course, correspondingly, if you want to talk about x squared times dA and integration, that is also called the moment of inertia with respect to y-axis. Okay, so these two are the fundamental definition of moments of inertia. Many times you cannot integrate out by these two integral forms. So instead, you just need to know what is the moment of inertia with respect to the axis passing through, going through the centroid. Okay, and that is the special moment of inertia. Typically, we call Ix bar and Iy bar. So once we know these two basic moments of inertia, then we can calculate the moment of inertia at any given axis we like, because of this important parallel axis theorem. From this parallel axis theorem, we can calculate the moment of inertia at any given axis you like, as long as you know the distance between this axis and another parallel axis passing through the centroid. So in other words, we do need to know D, and once we know D, we can easily calculate the area of this any geometry, because that's the mass concept. No matter what, the area is supposed to be the mass concept, right? And then we can use this equation to calculate out the moment of inertia with respect to this axis, which is equal to the moment of inertia with the special axis passing through the centroid, but parallel to this one, plus the area times d squared. And that is the theorem we called parallel axis theorem. With this one, we can calculate typically the moment of inertia of pretty much all the special cross-section area. For example, I briefly talk about this case, right? So typically in real engineering structures, we frequently use the wide flange. Sometimes we use the standard S, and sometimes we use a channel that's called C shape. Sometimes we call it angles. But no matter what, these are the simply combination of rectangular cross-section areas. So in other words, as long as we know the moment of inertia of this rectangular cross-section area, then we can apply the parallel theorem to calculate anything like this. And last time, I believe I spent some time to talk about this one. Okay? And some students ask me, do I need to worry about the curve here? You don't need to do that. You basically just assume this is the rectangular shape. There's another rectangular shape called a stem, and this is another rectangular shape. It's called a flange. Okay? So today, I'm going to talk about another example, just trying to show you how we can somehow take advantage of the charts typically we can get from this textbook, or typically we can get out. There's a lot of different categories in it's called the LRFD Design Handbook. LRFD stands for Load Resistance Factor Design, LRFD. Which is our kind of steel structure Bible in civil engineering, because basically it is very thick. There's more than 1,000 pages with all the information you get. If you want to become a structural engineer specializing in steel structures, That's really your Bible. You just have to look at it almost every day. Okay, so let me talk about this example and to see how we can calculate the moment of inertia. Okay, so we see this cross-section area something like this, which is a combination between two small geometry. One is a rectangle on top and glued with another, this is, you can call, it's not wide flange, it's called standard, I believe. It's called what, they should tell you somewhere. Okay, this W14 by 38. Okay, so the strength of W14 by 38 rolled steel beam is increased, is further, this one itself, this one, without talking about the top panel, this one itself is called standard, we'll call the W14 by 38 steel beam cross section, but this is further strengthened by putting additional top rectangular panel on top to increase the strength and also the rigidity as well. It's further increased by attaching a plate, a rectangular plate on the top to his upper flange, this one. Okay, so now we need to calculate the moment of inertia and the radius of gyration, which I'm going to give you some kind of definition. This is, once you know the moment of inertia, you can calculate the equivalent gyration radius. Okay, with respect to an axis which is parallel to the plate, that means parallel to the plate, but passes through a centroid of the section. The centroid of this whole section, not the centroid of this lower part. Okay, so then basically this one, we have the several things we have to figure out first. Okay, for example, what is that axis passing through the centroid? We were not given directly. You say, well, this point, this one, but we didn't give you from here to here is what? Or from here to here is what? We don't know it. Okay, and definitely the centroid of this whole structure is not the center point of this lower part. It's not here. You have to consider this part. So that's why we have to go over what we had in chapter 5 to have this problem completely solved. Okay? First of all, I would like to talk about this. If they gave you a certain designation, for example, you call the beam structure with a W something by something, then you just need to go back to look at your textbook. And I copied this chart for you. So if you are given with the cross-section with a W14 by 38, then what you need to do is to go back to look at this chart first to see if there is a designation having W by 14 by 38. We do have one. See here, W14 by 38. I want to make sure it's correct, right? Yes. So, but just in case you couldn't find this one, definitely you can find one from the handbook. Okay, but of course we are relying on this textbook, so definitely we need to choose something from this textbook. The designation for W14 by 38, so that means if you're having this kind of shape, instead of calculating the moment of inertia by yourself, which is a combination of these three rectangular shapes, you can take advantage of the result directly from the book. So in other words, for this W14 by 38, in fact, we know everything. We know the area of this cross-section, which is 11.2, is given here. And we also, if you want to know the specific geometry we're given, we don't need to use this one. However, we do need to know this is I bar, which is the moment of inertia passing through its own centroid, which is 355, right? And also the moment of inertia with respect to y-axis, that means this one, which is 26.7. Okay, and this K are something else we want to talk about, we didn't introduce. Okay, so in other words, going back to this example, we already know the moment of inertia of this one. Okay, so we can calculate the local moment of inertia of this one directly, and we also know the moment of inertia on the top panel, rectangular panel. So now it is our job to combine these two, localize the moment of inertia together by using the superposition rule. Okay, so first of all, we need to first calculate the centroid. So with this given cross-section geometry, okay, we need to locate that point C, which is the centroid of this whole structure. By the way, you may say, how do we know this one? So either they already gave you all the geometries, or you can find out from the chart. For example, for this one, W14/38, you have a 14.1, 6.77. So that's why I have a 6.77. From here to here is 14.1. Easily, you can use this number directly, or you can get it from the chart. But this, on top of this one, you have a thin plate. The width is 9 inch, and then the thickness is the 3/4 inch. Okay, so first step, we need to identify the centroid of this overall structure. And we need to go back to look at chapter 5. How are we going to calculate the centroid of a relative complex structure? Okay, again, we're using superpositions. So this one should be split into two simplified structure. One is the rectangular geometry on the top, and the other one is typically W14/38. Okay, and in order to calculate the overall x bar, y bar, which are related with the centroid, what we're going to do is to make a chart. So the first column, we can write down the two components. The top one is called the plate, or you can call rectangular shape. The bottom one is called the W14/38, where you give whatever name you like, called the beam section, for example. Okay, followed by another column is what we call A, which is area. Okay, so just in case some of you forget whatever, you can go back to look at chapter 5 slides. So this is the column to write down the area. What is the area of this plate? And that's very simple. That's going to be 3/4 times 9. So 3/4 times 9 is 6.75. And the unit is inch squared, because we have inch by inch. Okay, so that's simple enough. What is the area for the second one? Well, the area of the second one is a little bit difficult if you really want to calculate. But again, I was telling you, you can take advantage of the result we got here. They gave you the area directly, 11.2. So that's why you just write down 11.2 directly. Okay, any questions? Alright, so that's the easy part, right? And by the way, both are positive, because this time it's not something we subtract. If we are doing something subtract, then you need to put additional negative sign in front of the area, as basically we did in chapter 5. But this one, you just simply add them together, then that's perfectly fine. Now, the next column, we're going to talk about y bar. You may say, why not x bar? Well, we'll talk about x bar if you really like, okay? Because x bar is very simple to identify. So let's talk about y bar. Y bar, what is a y bar? We need to first figure out what is the coordinate system for this x bar, y bar. They forgot to plot the coordinate system for this one, but let's take advantage of this one, the same thing. For whatever, maybe this is referred to this one, in fact. Okay, so this is the original picture, but this is the picture we call the superposition. So first of all, we are going to set up the horizontal axis called x bar, x, and then the vertical is called y. The original point is the center of this lower part. Okay, so this lower part. And the centroid of the whole structure is here. That's what we call x bar. So we need to identify this C. So that's why from this C to O is what we call y bar, right? Because it's in the vertical direction. You may say, what is x bar? Well, due to symmetry, x bar has to be equal to 0. So that's why we don't list x bar here, because it's going to be finally equal to 0 for the global one. That's why we only want to have y bar. Now, for each component, for the plate, right? For the plate. So then what is y bar? With corresponding to this coordinate system, original point here, y bar for this small part, that's from the center to here. So the total from here to the top, from here to here is 7.05, right? So let's say from here to here is called the 7 point, this is divided by 2, in other way, right? 7.05. And then half of the thickness. The thickness is 3 inch. 3 inch divided, 3/4 inch. 3/4 inch divided by 2, that's a 3/8. So 3/8 plus 7.05, that should be 7.425. Okay, any questions? That should be simple geometry, right? Again, this number is obtained based on from O to this, the bounding point, that is the 7.05, plus half of this small height, which is 38. And it should be 7.425. And that is y bar for this grid area. That's why you put it here, 7.425. What is the y bar for the second part, which is the W14 by 38? Well, because you set up the x and y corresponding to the center of this lower part, then obviously y bar is the original point. That's mean equals 0. Okay? That's why you put 0 here. Any questions? Okay, so once we got y bar for each component, then we are going to have y bar times a. So then this one times this equals this one. So second row, 0 times anything equals 0. And then you can add all a's together. Summation of a equals to this, and summation of this one equals this. Then look at the composite rule, right, in chapter 5. So the summation of this divided by this, that's equal to the capital y bar. So capital y bar is the centroid, y component of this overall geometry cross-section. Okay? So you just put those numbers here, divided by 17.95, you get a 2.792. So this is y bar for the global cross-section. For example here, then from here to here, that should be 2.792 inch. Any questions? So again, all these slides, materials we're talking about, are based on chapter 5 principles, in fact, right? Because that's only the first part, to identify the centroid of this global cross-section. But once we identify so-called y bar, then we are going to move to the next to calculate the moment of inertia with respect to x-axis and later on with respect to y-axis. So again, one comment down to say, you may say, why are we only calculating y bars? Why we are not calculating capital X bars? The reason is the capital X bar for this structure equal to 0. Okay? Question?
How is the y bar for beam section 0?
You mean this one?
Yes.
Okay. Okay, going back to look at this picture. Keep in mind this second row, I'm talking of the local y bar, that's called the lowercase y bar. The lowercase y bar with respect to the second geometry, with this W14 by 38. Now, for this one, we are picking x and y passing through the centroid or the center point of this second part. Then let me ask you, this O, point O, this point O is the centroid for the W14 by 38. If this original point is also the central point, then what is the local x bar? What is the local y bar for that second structure? That's 0, 0. So that's why this is equal to 0. Any other questions? Okay. So finally, we get this y bar calculated through this way. One comment I just mentioned, the capital X bar. For those of you who are supposed to think about what is the capital X bar. So again, I'm telling you, the capital X bar equal to 0. Okay? It's not something we don't want to use. It's something you can easily find out due to symmetry, because this is the capital, this point, right? This point, the global centroid. The global centroid based on this coordinate system, x, y, from C to O is called the capital Y bar. But let me ask you, what is the x components of this point C? What is the x component of point C? That's x bar, and that's equal to 0, because it passes through y-axis. Okay? You have another? Anybody have other questions? Okay, so this is the first step. We identified the centroid of this global structure. Now let's move to the next one, which is to calculate the moment of inertia. Okay, so there are two moments of inertia. One is called the moment of inertia with respect to x-axis, and one is called the moment of inertia with y-axis. Now let's go back to look at what's the original question we were asked. We need to determine the moment of inertia, I forgot about the second one later, with respect to an axis. This is the axis, okay, defined as parallel to the plate and pass through the centroid of the global section. This is the section for the whole thing, not for the second part. So in other words, we are calculating the moment of inertia, the moment of inertia with respect to this x prime axis. Do you accept this? We are not going to calculate the moment of inertia with respect to x-axis. Why? Because the question asks us to calculate the moment of inertia with respect to an axis which is passing through the global centroid. This is the global centroid. That's why it's called x prime. It's not this one. Okay? So our final goal is to calculate this one with the moment of inertia with respect to x prime. But in order for us to calculate x prime, we do need to calculate the local moment of inertia with respect to each small area and add them together. So that's why, first of all, we want to calculate the, let me see. So we need to split this problem into two parts. One is the moment of inertia for this second part, I believe, or the first part. This one is the moment of inertia with respect to the second part. This one, W14/38, with respect to this x prime. And then we need to calculate the moment of inertia of this one with respect to the same x prime. Once we are done with these two, whatever number we got, we're going to add them together, and that is our final answer, which is the moment of inertia with respect to this x prime for the entire structure. So again, this plus this is called the superposition. Okay? So now let's do it one by one. So let's first calculate moment of inertia with respect to x prime based on this second component. We call W14/38. Okay, forget about this top rectangular shape first. Okay? And obviously we don't know equal to what. Because if you look at this local W14/38, the moment of inertia to the x prime, we have no idea. But we know the moment of inertia of this second part with respect to this local x-axis. Because that's, this point O is a centroid for the second part. Okay? This is a centroid for the whole thing. But this point O is a centroid for the second part. So then what is the moment of inertia corresponding to x-axis passing through the local centroid, the second part? That is W14/38, this one, x. This is the local centroid. What is that? 355? Okay, so I'm sorry, it's 385. Double check. My eyes are not that good anymore. 385, okay, and make sure the unit is inch force power. So this is the number we got from the previous chart. Okay, number one. Number two, we need to use the parallel axis theorem to transfer this one to this. Again, what is this? This is the moment of inertia of the second structure with respect to x prime. We know the moment of inertia with respect to this one, then we need to add AD squared. AD squared. What is A? A is the area of this second part, with the W14/38. What is the area of this one? 6.75. So we put 6, wait, I'm sorry, not this one. This one, the second part, 11.2, okay? So that's why we put 11.2, that's A, times D squared. What is a D? D is the distance between these two parallel axes. Okay, we just calculated from here to here. That is our capital Y bar, which is 2.792. So then 2.792 squared. So this add them together, which is equal to 470 something. This one is the moment of inertia with respect to x prime for the second part only, for this part, W14/38. Any questions? Okay, I hope I'm not confusing you, but you really have to do it step by step. Otherwise, you may forget what you were doing before. So, once we get this one, we recognize this is part of the moment of inertia for the whole thing. We leave it there. Now we move to next one, which is this. we have a rectangular cross-section area. What is the moment of inertia of this small rectangle? Again, with respect to x prime. Okay? Which is equal to, again, the moment of inertia with its local centroid axis. The local centroid axis is passing through the center of this one here. This is 1 over 12. 9, this is 9 times 3/4 inch, okay, because this thickness. This is called B, this is called H. Okay, so 1 over 12, 9 times 3/4 cube. You may say, what is the formula we're talking about? Well, just in case you forget, I'm going back to show you this. And this is the only one I'm asking you to memorize. Okay, so I'm asking you to memorize only these two. Nothing else for this chapter. But it doesn't mean I'm going to ask you something else. I'm asking you something else definitely based on these two equations. So 1 over 12 BHQ. BHQ, right? BHQ. Okay? If you're talking about with the y-axis, that's 1 over 12 B cubed H. Because once you know these, you can pretty much deal with almost anything you like to do, in fact. Okay? And you go back to look at those 4 questions you are going to turn in on this Friday. These are all related with this one. Okay. Going back to this one. So the local moment of inertia with respect to the local centroid of this rectangular shape is 1 over 12 BHQ. This is the B, which is 9. H is 3/4, and then Q. So this part is in this local moment of inertia. And then plus, again, using the parallel theorem, plus AD squared. Again, what is A? A is the area. That's easy enough, right? So 9 times 3/4. 9 times 3/4 is 6.75. That's A. Then what's the D? What is the D? D is the distance between these two parallel axes. So this is one axis, this is another one, and that's D. They already indicate this is D. So what is the D? So this D is basically okay, so there's many ways you can identify D anyway. So maybe one way I can say is from here to here, okay, and then minus this part. So 7.425 is from here to here, and then minus y bar. So 7.425 minus 2.792. And that's D. And don't forget with the square here. And then you punch your calculator, you get another number, 145. And the 145 into the 4th power is the second moment of inertia with respect to x prime based on this rectangular cross-section. That's the second part. So once we know the first part, we know the second part, now we use a superposition rule to simply add them together. Why can we add these two numbers together from physical point of view? Because both are moment of inertia, and more importantly, you can add them together because each of them is corresponding to the same coordinate system, which is called x prime. This one is corresponding to x prime. This one is corresponding to x prime. That's why you can add them together. For anything you use a superposition, whether in chapter 5 or in chapter 9, this chapter, you need to make sure any number you calculated should be, if you want to add them together, you must make sure they are talking about the same language. In other words, they have the same coordinate system. So that's why this one is x prime. This one is also x prime. So they can communicate directly. Okay, and that's a requirement for any of you who want to use the superposition method. Okay, so finally you can add them together, and that is called I, the moment of inertia of the whole structure. Okay, for the whole structure with respect to x prime axis. And this x prime axis is passing through the centroid of this global cross section. Any questions? Okay, one more thing. We are asked to calculate the radius of gyration with respect to this moment of inertia. So I just want to give you the definition. This is the definition of the radius of gyration, because I think the homework question probably asks you to calculate the same thing. But don't worry about that. As long as you can calculate moment of inertia, you need to divide it by the cross-section area and then take the square root. And that is what we call gyration of radius of gyration. Any questions? Okay. So this is another example just to typically show you, just in case, if you were given with a specific wide flange or standard or channel or something, again, you can use a superposition, but obviously you can take advantage of this chart. You may say, well, I'm not asking you to memorize this because there's no way you can memorize those. Then the simple question is, are we going to have some kind of question in the final asking you to do something like this, the combination? Well, think about it. I can define a certain, like S10 by 25 or W8 by 31, and I gave you that chart, right? Then you still need to do it. Okay, I'm not asking you to memorize these numbers because that's not the thing you're supposed to memorize, because you're supposed to get it from the handbook. But of course, the final exam is a closed book, right? There's no way you can look at the handbook, but I can give you some numbers if I need it. Okay, so that's why I'm pretty sure typically for those structure, you just need to memorize this. But it doesn't mean you can only calculate this one. You can calculate many other things using what we call the parallel axis theorem. Chapter 7 mainly talk about forces in beams, but they do have another topic which is called the forces in cables. So I'm going to briefly talk about this one. It's basically the special thing in chapter 4, but we just need to identify one more question. Okay? So you can frequently see a lot of cable problems, in fact. Okay? So obviously there's one person walking on the very, very slender cable, okay? And then if you want to calculate the strength or you want to calculate the force in the cable, then this is something you can do just based on our current chapter, chapter 7. Okay? Now, simplifying that scenario, we are basically talking about something like this. Okay, so for example, you have a cable. I didn't give you the whole picture. Most likely this cable somehow clamp over here, the other end clamps somewhere here. So then what I'm trying to say is, okay, you do have a cable A, C1, C2, C3, B. So cable AB, okay? So this is the cable AB, and then on the one side is the pin end supported, and the other side is another pin end supported. This cannot be rollers, by the way, okay? Because this going to give you the restriction in any two directions. That's why both are pins. Okay? In addition, there's some kind of concentrated load acting in between. Okay? So now, how are we going to calculate the reactions, and how are we going to calculate the cable force? Talking about the cable force, then you're going to make some cut. Okay? But before talking about the cable force, which need to be calculated by cutting somewhere, let's first probably need to calculate the reactions. And we know that in chapter 4, or even in chapter 7, in chapter 6, how are we going to calculate the reactions? That's supposed to be simple. We just cut those reactions, right? We cut point A, we cut point B, and we plot the free body diagram. Okay? Let's follow what we have learned. So this is the cable AB again. But we cut point A, we gave two reactions, right? So these reactions are called AX, AY, which are unknowns. We know that. And then we cut point B, which is another pin, and then we gave another two reactions. Okay? And assuming we know these forces, let's just put those forces here. Now, this is what we call the free body diagram for the entire structure. The question is, for any given this kind of two-dimensional, you have to agree that's two-dimensional, right? How many equations we're supposed to generate? We can generate 3. Okay? If you go back to look at chapter 4, right? We always talk about the independent governing equations or equilibrium equations for two-dimensional problems are 3. 2 force equations plus a moment equation. But now, when you look at this free body diagram, how many unknowns do we have? This time we have 4 unknowns. Okay? So, obviously there is a challenge in general. We cannot have enough equations. We want 3 equations, but we have 4 unknowns. Okay? So if you were encountered this kind of problem before, then the simple way you can say is, let's give up. Because we don't know how to do it. But now this time I'm just giving you a trick because that's specifically for cables. It does not work for beams. It's for cables. For cables, you can in fact generate another equation. And in fact, that's also the special case as we talked about before in chapter 4. That's called the two-force body problem, in fact. The reason is this. At anywhere you want to cut, for example, right? At point D, you want to cut. You want to cut. At point D, after you cut, there is no moment at that point. If there's a moment, internal moment, you typically want to have beam. For example, going back to look at any picture you had in chapter 7, right? When you have a beam, when you cut it, then after you cut, you need to give an internal moment. That's called M. But if this is a cable, there's no internal moment because it's very flexible. So that's why when we talk about cables, I highlight here. Cable is flexible. In other words, namely, resistance to the bending is very small. Very small means you ignore it. Okay? So at any point, if you want to make the cut, then let's say we cut point D. Once we cut point D, the whole structure is split into two parts. You pick whatever part you like. For example, we're going to look at the left side. Okay? We're going to look at the left side. When you look at the left side, we have still A here. You have an AX, AY. Okay? And you cut here, which is to the right of C1. Then you still need to give at C1, there's a force P1. Just put it here. Now you cut it at point D. Once you cut at point D, there's an internal force. Obviously, that's right. But the internal force is going to any direction you like to say. However, there's no internal moment. Okay? And actually, you know what? This one, it has to be, is a two-force body. It has to be going through that direction. So now, let's going back to look at this new free body diagram. This new free body diagram. New free body diagram. How many unknowns do we have?
3.
We have 3 this time. See? 1, 2, 3. So we can still have 3 equations. Especially, you can collect all the forces in y direction set equals 0. You collect all the forces in x direction equals 0. And then you take a moment equation. For example, you take a moment equation at point D, or you take a moment equation at point A. Then you can solve for these unknowns. So that's why after we make a so in principle we have 4 unknowns. There's no way because we only have 3 equilibrium equations for the entire structure. That's why it is not sufficient to determine all the reactions. But that's fine because this is the cable problem. Then what we're going to do is we're going to create additional equation. So that additional equation can be obtained by considering an equilibrium of part of the cable. For example, point D, you cut a D, you look at AD part. Of course, you can look at the DB part, it's not a problem. Just look at one part. And then after you make the cut, there's no moment at point D. So that's why you can take a moment of all forces at point D, then there's one equation, and then you collect all the forces in x direction, you collect all the forces in y direction. The bottom line is you can calculate all the unknowns. Okay, so this is the principle to solve any cable problems. Now I'm going to just give you an example, just to show you specifically how we can solve specific problem. We have a cable like this. Okay, you can think about this kind of like a cable car, right? If you travel to Palm Springs, you basically see this. Of course, this is very simplified. At point A is pin support. At point E, there's another pin support. All the geometries are given. Okay. In addition, there are 3 forces, concentrated load. It's like a tram or cars located in different areas. Then we need to calculate the reactions. We need to calculate the cable forces. Okay. So geometries are pretty much given. So cable AE, the whole thing, support 3 vertical loads. 1, 2, 3, with a given 6 kips, 12 kips, and 4 kips. By the way, kip. 1 kip is what? It's 1,000 Newton, 1,000 pounds. Okay. So cable AE supports 3 vertical loads from the point indicated above. If point C, see this point C. If point C is 5 feet below, 5 feet below this, the left support. So this is the horizontal line. It's called the left support. For example, it is 5 feet below. So from here to here is 5 feet. Then we can determine the elevation of point B and the point D. So what is the elevation of this one? In other words, this one. And what is this? Okay. So in other words, the elevation of this, you don't have to know it. You can calculate. Of course, we should be able to calculate the reactions as well. Okay. So typically, for this kind of problem, if we know at one point, we know the location. In other words, we know at point C that's 5 feet below, then what we're going to do is cut at that point to generate one additional equation. So we cut at point C, then the whole structure is split into two parts. You pick whatever part you like. Let's pick the left side. Okay, so again, I'm sorry. So again, you look at the entire structure, you cut at point A, you gave two reactions, you cut at point E, you gave two reactions. There's no way you can solve for four unknowns because there are only three equations. That's why we're going to cut at point C. So once we cut at point C, we look at this part, A, B, C part. So then what we're going to do at point A, again, you have two reactions. Point B, you still have this one. At point C, you cut here, you gave additional force. But you also have this 12 Kips acting on point C, right? So this is what we call a free body diagram on this part. Then what we're going to do is to calculate the reactions first. How to calculate reactions? Well, there's many ways because you have three equations anyway. You can use whatever you like. For example, we want to collect the moment of all forces at point E. Where's, I'm sorry, not this one. Look at this point C. So let's take a moment at the point C of this structure. Take a moment at point C. These two forces will not be involved. That's fine. But you have AX. So AX times the shorter distance from here to here. That's a shorter distance. AX times shorter distance 5. AX times 5. And this is going to be clockwise on this rigid body, right? So that's negative. So this is the moment due to AX. And then what is the moment due to AY? So that's going to be AY times the shorter distance from C to here. That's going to be 10 plus 20, 30. So 30 times AY is also clockwise. So put a negative sign here. So this is the moment due to AY. And then what is the moment of this force at point B, which is, what is the 6 Kips, right? So 6 Kips times the shorter distance from here to here, or C to here, that's 10. So 6 times 10, that's the moment. But this is a counterclockwise. That's why you put a positive sign. So this is the equation you can generate based on the moment at the point C. This is the one equation. You can easily write down other two equations by collecting all the forces in X direction, all the forces in Y direction. However, if you want to go back to look at the original overall, what we call the overall structure, then even though you have four unknowns, but if you want to take a moment at this point E, then you are only going to have AX, AY involved in that equation. If that's the case, you can combine these two equations to solve for the two reactions, AX, AY. So let's take advantage of this overall free body diagram and take the moment of forces at point E. EY, EX will not be involved because they are going through this point, but you have the moment due to force at point D. That's a 4 times this one with a 15. 4 times 15 is counterclockwise, so you have this term here. And you have a 12 Kips multiply 15 plus 15, 30. 12 times 50, 30, that's also counterclockwise. So 12 times 30, that's another moment due to this. And you have the moment due to this for 6 times 40. So 6 times 40, and also counterclockwise. And finally, you have the moment due to AX. That's going to be counterclockwise, AX times a 20 inch. So AX times 20 inch, that's a moment due to AX. And you also have AY times this shorter distance, 20, 10, 30, plus 30, 60. So 60 times AY. But this is a clockwise. So that's why you have a negative sign. So you are simplifying this equation, you end up with this. This one need to combine with another equation we just generated, these two equations, to solve for AX and AY. Right? So from AX and AY, you can basically calculate, from these two equations, you can basically calculate AX and AY. Now, after you get AX and AY, can you calculate EX, EY? That's not a problem. We did not write here. But obviously, that's not a problem, right? Going back to look at this entire free body diagram, you need to collect all the forces in X direction. In X direction, what is the EX? EX equal to negative AX, correct? Because there's only two forces in X direction. If you want to calculate it, so AX is finally given negative 18. Negative 18 means what? Negative 18 means AX is in fact to the left with a magnitude called 18 Kips. What is AY? You calculate AY, which is 5 Kips. That means AY is going up. but the magnitude is 5 kips. So if this AX is to the left with the 18 kips, then what is the EY? EY is going to be to the right with the same magnitude, 18 kips, because there are only 2 horizontal forces involved. Now, you know AY, which is 5. So this is the 5, but going down 6, 12, that's 18 plus 4, 22. So all 3 forces going down 22, 1 force going up 5. Then what is this force? This is going to be 22 minus 5, 22 minus 5, 22 minus 5, 17. Right? So EY is going up. The magnitude is 17. So the bottom line is you do need to create a new equation in order to solve this original problem. And that new equation is basically you need to make a cut at a certain point which you know the location so that you can generate this moment equation. Okay, so that's the first part. We calculated the reactions. Now, the question asks us to calculate the elevation at the point B and the elevation at point D, the location, but with given forces. So next one, what we're going to do, but this time we already get those AX, AY, EX, EYs, right? Next time, we need to calculate the elevation at point B and the elevation at point D. So let's say we have this part, we cut it at point B, because you want to calculate the elevation, you have to cut at point B. Once you cut point B, you look at the left side, you have AX, AY, which are calculated before. And at this point, you cut here, you got a BY, right? So how to calculate BY? So basically, you just take a moment at point B so that you don't need to worry about this cable force. Of course, if you need to calculate cable force, you need to use additional 2 equations. If you only need to calculate the elevation, then take a moment at point B. So now these 2 forces are not being involved because both of them are passing through that point. So basically, you have 5 kips. So 5 kips times 20, 5 kips times 20, that's clockwise, so there's a negative sign here. And then the moment due to this 18, so 18 times YB, because that's elevation. And that's counterclockwise, so YB times 18. And minus this moment due to this force, that's supposed to be 0. And from this equation, you can directly calculate YB. So YB, based on your calculation, is negative 5.56. Negative 5.56, that means what? This one actually is going up. Let me see. Wait, I'm sorry. I don't like to write this way. Okay. From this equation, in fact, YB equal to positive 5.56, I believe. Because here, this one times this minus this one equals this. This YB, in fact, is what? YB, in fact, is a positive 5.56. But I know the reason why they put a negative sign, because they want to indicate it's below that. But the reason you cannot get a negative because you assume this YB is below already. Right? Because the YB you plotted, point B is already below point A. So that's why this YB, based on your calculation, should be positive. If it's a positive, then in fact it's below. So that's why their final answer is a negative 5.56. Means point B is below point A, and the distance between A and B in the vertical direction is positive 5.56. The distance. But we're talking about elevation is supposed to be going down. So that's why they finally put negative 5.56. But what I'm trying to say is these 2 things are not consistent. Okay? Anyway, so this is the final answer. Similarly, you can also calculate elevation at point D. So we need to cut at point D. Now we're looking at this one. So this time we assume point D is elevated up. And that's dy. So same thing, you are going to collect the moment. There's a mistake here because there's supposed to be a moment at point D. They forgot point D here. That's supposed to be at D. Because you take the moment of all forces, you need to give they were written here, right? It's not written here. So this is D. Okay, so moment at point D. So then these 2 forces will not be involved. You have this 18. So 18 going to be clockwise. 18 times dy. 18 times dy is clockwise. And then 5 times 30, 45. 5 times 45. 5 times 45. That's going to be clockwise. That's why negative sign. This one is 6 times 25. 6 times 25 counterclockwise. That's a positive. 12 times 15, which is also counterclockwise positive. From this equation, you get YD. So YD, because we assume going up, and from this equation, you calculate positive. So that's why the elevation is positive 5.83. Any questions? So this is basically the typical cable question. Your strategy is to create one more equation, and that equation is obtained by making a cut at a certain point. You know the location. For example, like this one, you need to cut at point C, because the point C, they gave you the location, which is 5 feet below. That's why you need to cut point C. You may say, can I cut anywhere else? You can cut it, but you won't solve the problem, right? So that's why it's useless. You just have to cut at point C, because the point C, you happen to measure the distance, or called the elevation. And once you know that, you can make the cut, and you can solve the problem. Okay? So this is the first part I call forces in cables. And all you need to do is to generate one more equation. That's a moment equation after you make the cut. Okay, the other part I want to briefly mention is the chapter 8 talking about the frictions. Okay, you already know from college physics, I think like physics 7C or something, no matter what you learn, even in high school. Frictions are everywhere, basically, right? So many of them are bad, but many of them are good as well. So that's why we say the friction is both problematic, but also sometimes it's very useful in many engineering applications. Okay, for example, you have this kind of a brake when you ride a bike, or you have this space shuttle. This is a launching or a landing, I don't know. Anyway, there's a friction related. Typically, when we talk about simplified engineering problems, when you have a block on the surface, okay, so if there's no horizontal forces, there's no friction needed. Okay, however, once you apply a tiny force in the horizontal direction, then obviously there will be a friction. Okay, assuming the surface is now smooth, right? So now, typically, when you keep increasing the P, then the friction will increase. The friction will increase. So in the static scenario, the friction would increase until it reaches the maximum. Then this one starts to move. Once this block starts to move to the right, then this is called a kinematic, right? Kinetic friction force will be a constant. Before its movement, the friction force resistance keeps increasing until it reaches the maximum. The maximum can be calculated with this, what we call the static friction force maximum, multiplied with the pressure, which is called this end, right? Okay. And once it moves, you are no longer having the static friction force. Instead, you're going to have a kinetic friction force because it's moved. So then, this friction force is equal to coefficient of friction multiplied with n. But these are all you learn. I don't want to talk about this. Today, I want to talk about one more thing which you might learn, you might not learn. And the reason I want to point out this one, it's simple, but this many times for those civil engineering students, when you become a senior student, most likely you're going to take what we call the EIT test. And this is the part of the EIT test. Now, typically, you may encounter one simple example just to use that equation I'm going to show you to calculate something. You see, in many engineering practice, for example, you use this kind of cables, right? You use this kind of cables, okay, belt. This is called a belt friction, which is not part of this, because you learned this one, I know. But if you are talking about something like this, to control a big boat or a ship using this one, obviously from common sense, the more circles with this belt, the better, because it gives you more friction. But you may say, how much? Right? If you want to quantify the friction, then this is something we need to deal with. Okay? And sometimes you see when you're trying to hand on a crane, for example, you may have more circles with this cable to increase the friction. Okay? The bottom line is, once you have a belt passing through a circle, a wheel, or a pulley, for example, then you need to know how to calculate the friction between this contacting angle, which is totally called beta. It's called beta, right? Called beta. Okay? So in other words, if you ignore the friction, then T2 is always equal to T1 because there's no friction. But if you do need to consider the friction, then T2 is not equal to T1. But which one is bigger? It depends on which tendency this will try to rotate. So if you're trying to rotate to the right, then T2 will be bigger than T1 because you have to overcome the friction. Okay, and this is the general scenario I want to talk about, and to finally give you this equation between T1 and the T2. Okay, so anytime when you are dealing with any of this kind of problem, as long as you have this equation, you can quantify the friction force. You may say, wow, wait a second, this is only I'm talking about something with a beta less than 180 degrees. Now I'm talking about this one. What kind of angle we need to say? One circle is 360. If you have two circles, then what? Times 2. You have 3 circles times 3. And you have a 3 circle and a little bit more, then 3 times 360, and then plus another angle, 30 degree, 50 degree, whatever. Okay, so that's why the more circles you use the cable, the better, because you provide with more friction. Okay, so back to this one. We are trying to use a relative simple statics, because this is a static course, right, to derive this equation. Same thing, we basically use those equations, okay? So let's say we have this scenario with a T2 going this way, T1 going this way, T2 going that way. But you need to know it is about to slide to which direction. So if we assume we want to relate T1 and T2 when the belt is about to slide to the right. So it's about to the right, then T2 need to overcome not only T1 but also the friction. So obviously T2 is bigger. Okay? Because T2 should be equal to T1 plus this kind of friction resistance. The bottom line is how we can get this equation. That's a typical we do by making a very small cut on the top. And then we do the integration. And then we solve the problem. Like making this small cut with a delta theta. That angle is very small. You have this part, belt. And then we have a T, and we have an additional T. So this additional T is T plus delta T, which is kind of overcoming the friction part. So delta T, or say, I'm sorry, this T prime is T plus delta T, the increment. In addition, at this point, there is a reaction because of the wheel. You call this delta N. And there's a friction here, right? It's very small. We just assume the friction is horizontal. Later we'll do the integration. So this friction equal to the normal force multiplied with the friction coefficient called the mu s times delta n. So this is what we call the free body diagram. What you need to do is to collect all the forces in x direction and set equal 0. You need to collect all the forces in y direction and set equal 0. That's a typical static equations, right? You may say, what is the third equation? Which is the moment equation? Well, if this keep decreasing so that delta theta will be very small, then this part of the rigid body become a particle. So that's why you can still write down the moment equation, but it becomes a trivial equation, the 0 equals 0. It doesn't work. So that's why you only need to use these two equations. From these two equations, you can just consider this very simple concept, in fact, right? You just collect all the x component together, all the y component together. Now, combining those two equations, you need to get rid of delta n first, because this delta n is something we don't need. So we want to build a relation between t and t prime. So from these two equations, combining them, you need to eliminate delta n, then you get this one. And then you need to keep delta theta smaller, 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 smaller until it reaches 0. Then it become delta t become dt, and the delta theta become d theta, and minus this one equal to 0 based on this equation. And this is a differential equation. You integrate out, then finally you get this one. So in other words, this log equation, you can get exponential equation, relation between t2 and t1. And this is not an equation I typically memorize. I would like to memorize this one, which is basically this. Because this is easier for us to memorize. This is the same thing with this one, but I just want you to somehow understand, in order to build a relation between this cable force and this cable force going through the friction belt friction case, then you need to measure this angle. Once you measure this angle, then you need to use the E exponential function, multiply the coefficient of friction, and multiply the angle beta. Well, they didn't draw beta. This is the beta. Or you still go back to look at the original picture. It's called beta. Okay? And then you can build a relation between these two cable forces. Okay? So typically, this is the equation you need to somehow know. Okay? In this textbook, we gave you this equation, but I'm not going to assign any homework, and I didn't talk about any examples. So this part and the cable part are obviously just for information. That's how I call it miscellaneous. Okay. But the strategy for solving such problem, I'm pretty sure you will use them in the later courses, especially for those of you who like to take this EIT test, or called the FE test, I believe now. It's called the Fundamentals of Engineering test. Typically, civil engineering students are taking it during your senior years. I do not know for mechanical aerospace, because civil engineering, they have a license requirement typically. If you want to do the consulting work after you graduate, you typically need to pass 2 tests. One is called the EIT test, and the other one is called the PE test. PE test, basically, you have to take it after you have several years working experience outside before you take the PE test.